And this is kind of like a follow-on to the demonstration I did last week. This is going to be focusing on using Envelope with SSKR. As you recall from last time, I went through the kind of an overview of what we'd like a general kind of container object, a digital container object to do, and it involved a lot of things, including being able to label it, being able to put a variable size, including small or large payloads in it, being able to transparently see through part of it, nest them with various kinds of credentials at every level, and so on. And as I pointed out, it's actually not hard to do that with a pretty simple generic structure, and this is what that structure looks like. Again, I mentioned this in the last one. This is Swift code here. And most of our reference code is in Swift. We also sometimes have C++ versions. In this case, so far, we've only done this in Swift. We're hoping the community will be interested enough in this to actually port it to some other platforms. So an envelope is just basically a subject and a set of assertions about that subject. So last time I didn't go very deeply into it. I just want to go a little bit more deeply into it this time, because I also mentioned last time that, well, what is an assertion? Assertion is a predicate and an object. And a predicate would be like, if I want to say A knows B or Alice knows Bob, knows is the predicate, Bob is the object, and in this case, Alice will be the subject. So Alice knows Bob. The subject is Alice, the predicate is knows, and the object is Bob. And so because we can have any number of assertions, we can make any number of assertions about Alice as well. And that can actually be used for things like semantic graphs and so on. There's a lot of capabilities built into Envelope. And one thing I didn't unpack last time is what is a subject. So the first field is the subject, Alice, right? So what can a subject be? Well, a subject actually is a enumerated type with 4 cases. It can be any CBOR type. So that could be anything that you can encode CBOR, which is pretty much anything. It can be another envelope that's been nested inside this envelope. So let me point out before I go on that this means that the subject, the predicate, and the object can all be envelopes. In other words, they're all recursive. It can be an encrypted message, which is you don't know what it is, but it's been encrypted, or it can be a redacted object. And because one of the things that the envelope also supports is digests. So you can basically, well, if you understand the concept of a Merkle tree, well, basically envelopes are a Merkle tree. So you can have a digest of the whole envelope, and you know that even if parts are redacted, it's still the same envelope. So you can have progressive disclosure, things like that. Things that aren't relevant to this conversation, but I just want you to know they're all there. So these 3 things together are basically the kind of core of what envelopes are. So at Blockchain Commons, we want to make sure that you have what you need to move forward using these technologies. And Christopher last week requested a set of test vectors from me. So basically, if you're implementing crypto envelope, if you want to know that you're incompatible, specifically with regard to SSKR scenarios, because you don't have to do the full envelope implementation. It's not huge, but you don't have to do the full envelope implementation, as I pointed out last time. But you do want to know that it's compatible. So these test vectors are currently living in our BC Swift Foundation repository in the documentation. Secure Components is our suite of basically kind of repurposable things like encrypted message and so on that you'll see. And if you want to access this, there's a long URL, but there's also a shortened URL, or you can just snap that QR code. I will also put that into the chat, or somebody will. But this is where the actual test vectors live. But I just want to kind of unpack a little bit about a couple of them, just so you can kind of understand, when you see this long page of test vectors, you'll get a better idea of what's actually there. So the first thing, obviously, when you're doing test vectors, reproducibility is key. And so I want to talk briefly about the sources of randomness used in generating SSKR shares, because I had to fix them in place to be able to do repeatable SSKR shares, because normally you don't want to do that. Remember, seed tool warns you that if you regenerate these shares, they're going to be different. So there's actually 3 sources of randomness used for SSKR with any size payloads. One is the symmetric keys for encryption. Our secure components currently use the cha-cha poly algorithm, and that uses both the symmetric key and a nonce, and these are the fixed values I use for those for the test vectors. And then SSKR itself uses a random number generator that you provide, and I've just provided a fake random number generator that returns this repeating sequence of hex values, so it becomes deterministic. So referring back to that page, so if you want to go examine this later, this is test vector 1. It's the seed split into 2 of 3. So we're going to look at this from a couple different perspectives. The first is from the perspective of the payload. The payload itself is a crypto seed. Crypto seed is one of our specs for objects encoded as CBOR. This is just like you see stored in seed tool. This is exactly what seed tool uses. It's got a seedboard tag at the beginning, 300, which represents crypto seed. It's got 4 fields. 1 is the seed, 2 is the creation date, 3 is the name, and 4 is the notes. Of these, only the first one is required. So the others are totally optional, and so the structure itself can be very small. So a quick recap of SSKR itself. The whole purpose of SSKR is to take some object, split it into any number of shares. In fact, you can have groups of shares as well, but we'll skip that for now, with a threshold, so that threshold or greater can be used to reconstruct the original secret, which doesn't have to be a seed. It can be anything, and that's part of what we'll get into in a minute here. Because if you don't make that quorum, you cannot construct the original seed. So you can safely hand these out to multiple parties and not worry about, and then have multiple groups. So even if you think the parties might collude, make it very difficult, but still make it very reliable and resilient that you can get your secret back. So what are we after in terms of what you give away? What's on those coupons? Well, ultimately, we want to have a UR. This is a UR crypto envelope. It's it's all basically ASCII text, and this is a way of encoding binary using a variant of the byte words standard. And this is, in fact, very optimal for encoding in QR codes for 2 reasons. One is that if you encode it in uppercase, it's actually more efficient than encoding base64. I've seen a lot of QR codes that contain base64. What a lot of people don't realize is you're leaving a lot of money on the table when it comes to base64, because you have 64 characters, but you actually have to use the binary encoding mode, which basically means it's 8 bits per character. Whereas what we're using is the alphanumeric encoding mode, where it's very efficient. It's almost it's about as efficient as you can be with binary in QR codes. The second reason is that because we are UR standard allows you to split QR codes into a non-repeating sequence of fountain codes. You can actually contain any amount of payload in a QR code that animates. And so you can, send any amount of data through an air gap, basically through your camera. Okay, so this is kind of the end result of this process. This is one of the 3 shares in the test vector. So let's look at it from what's called the envelope notation point of view. Envelope notation is just a very simple. Remember, I said that it's a subject and then a series of assertions, which are predicates and objects. And here we have the subject is an encrypted message. It's ultimately the SSKR. The seed payload that's been encrypted, and then it's got a predicate which says, here's an SSKR share you might need to decrypt this, and here's the SSKR share. That's the object. And you'll see this reflected when we look at the other things. So if you've studied CBOR at all, there's a standard kind of notation. CBOR is basically like JSON in binary, so it's actually more efficient. In many ways, it's way more flexible than text JSON, and binary objects can be encoded directly as binary. So in this case, what you see here are the tags here. 49 is crypto envelope. 48 is the crypto message, which is the encrypted message object. It's got 4 fields: the ciphertext, nonce, the HMAC auth, and the additional authenticated data. And then it's got this array here, which is the predicate and the object. And the predicate is here's an SSKR share, and the object is the SSKR share. This is what's called, again, CBOR diagnostic notation. There's websites like cbor.me. You can just plug some hex into it and it'll spit this out. That site also spits out what's called the annotated binary, which is basically the actual full hex with also the same kinds of annotations called out on it. And really, it's that simple. Now, I want to move on to into a related topic, which is that kind of just touches on some of the flexibility of envelope, which is vendor specific data. A lot of times, I want to avoid the impression that what I've just described here is a very rigid format that has no flexibility. In fact, it's got pretty much infinite flexibility. And to this, I want to point at test vector 2, which is a string that's been broken up into 3 of 5 with an additional assertion. And again, because those assertions can be anything, and they themselves are envelopes, they can be anything provided by the vendor. So here, let's look at the payload. It's just a string. And like I say, anything that can be encoded in CBOR can be a payload, can be in an envelope, can be a predicate, can be an object. So, I want to keep emphasizing that. In this case, remember the envelope notation. This is from the previous one where we didn't have an additional assertion, but here's our additional assertion. It's a note that in this case, it's a text. This could be vendor specific data attached to the envelope. And this could truly be anything. In fact, it could be whatever binary you want it to be, as long as it's encoded in CBOR. So again, I want to emphasize that this doesn't limit you in any way. Even the predicate can be whatever you want it to be. Here is that basic, the same, the test vector 2, share 1 of 5 in CBOR diagnostic notation. This section highlighted in red is just the part that's been added. It's the other assertion. And as you can see, it's got 2 crypto envelopes. One is the predicate that basically says this is a note, and the second one is the note itself. From the annotated binary point of view, again, here's the new section. Again, so adding as many assertions as you want of any kind. You can have assertions with assertions. So in fact, you can have many levels with different features at each level. You can have envelopes that are encrypted inside envelopes that are encrypted, each with different policies on them. And it's really up to you to decide how to do that. Obviously, we'd love you to share your work with Envelope with the community so we can all benefit from that. Before I finish, I also want to touch on another standard we're developing called Crypto Request. And this, again, we're designing all our standards to dovetail and work with each other. This is a way that you can simplify protocol design by defining the format of requests as UR, CBOR, and things like that. Where, for example, in this case, a device is making a request and closing it in an envelope and displaying that as a QR code. And then another device receiving that through its camera generates a response, which it then sends back through the internet, which is received by the other device. So there's no limitation on how these requests and response can be sent. Just because it comes in one direction, a QR code doesn't mean that request can't say, oh yeah, respond to this other URL and have it come back that way. So again, our as I mentioned last time, we want simple things to be simple and complex things to be possible. So if these things seem like they don't serve your needs for some reason, please let us know. And again, I'm always available on Signal or at wolf@wolfmcnally.com. And yeah, I look forward to your questions.